Hey everybody, it's Mr. Matthew here for AP Biology Video Essential Knowledge 4A6. And in this video, we're going to talk about interactions among living systems with their environments and how that results in the movement of matter and energy. So here we go. So what we want to do is we want to start with the idea of being able to apply mathematical routines to quantities that describe interactions among living systems and their environment, which results in the movement of matter and energy. And so specifically what we're going to look at in terms of mathematical routines is I want you to look at a concept we refer to as carrying capacity. And so for this, what we have is two graphs. We have in blue, we see a population growth curve that represents exponential growth. And in red, we show a population growth that represents logistic growth. And we see that that logistic or S-shaped curve is capping out around carrying capacity, which is symbolized as K. And so what I want you to do is I want you to pause and think. And the pause and think here is a species carrying capacity a fixed value, or is it a variable? Explain in your pause and think. So pause and think. So for this one, unlike a lot of my pause and thinks, hopefully this one jumped out and said, no, it's a variable. Like this thing can absolutely change. And so what we see here is that logistic growth is a calculatable factor. You can see that I've dropped that population growth rate is measured in the number of individuals in a population, which we symbolize as N over time, and our K is our carrying capacity, and that we have all of these other variables that are put in here that help us figure out how close to K we get and how this all works out. But this is showing that the carrying capacity K is 1,000. But certain factors, both abiotic and biotic factors, will influence the height of K. So if we're looking at this population, and this is a population of producers, it is going to be important to know how much available land is present. Is there competition from other producers for land in this area? If there's a limited amount of land, the carrying capacity is going to be limited. Similarly, there's other abiotic factors such as water that could play a role, or there could be herbivores or other consumers that could be consuming them. Those things can influence how big carrying capacity is. If we're looking on the consumer side, are there other organisms that are competing for resources? How much available food is present? How many places are there to live? When we look at how humans often impact carrying capacity, have we fragmented the habitat so that there's only small little areas where populations can grow, and therefore the carrying capacity is limited because we don't have large continual areas for these organisms to move and to feed and to grow and to find mates. So a lot of different factors can influence. As a result of those biotic and abiotic factors, our carrying capacity could change. All right, so what I wanted to be able to do is to use a visual representation to analyze a situation or solve problems qualitatively to illustrate how interactions among living systems and with their environments result in the movement of matter and energy. So in this particular example, I'm showing you a rocky shore community, and this rocky shore community shows there's a sea star at the top, and all of these different things, from barnacles to bivalves to limpets to snails, they're all being consumed by the sea star. And so what we'll see here is this is definitely showing movement of matter and energy, in this case the matter, the biomass, and the energy, where all of these organisms are they're being consumed by these sea stars up at the top. We're seeing the flow of energy in this case. So let's try to analyze the situation. What do you think would happen if I removed the sea star from this community? What do you think would happen to the species diversity in this community? So let's analyze a graph that shows two environments. One in which they maintain the sea star, and we'll call that the control, and then one community where they went out and removed the sea star from this environment. This actually was done by Payne in his study of this rocky shoreline. And this is what we see. In the control environment, the number of species that are present is really high. And in the area without, it's really low. So what do we think is going on with these sea stars? All right, so hopefully you are like, wait a minute, I know what this is. We see one organism that's really important to the ecosystem, And when you remove it, the ecosystem stability collapses. That is pretty much our definition of a keystone species. And so what we're able to do is visualize, both by showing some energy flow, by this energy flow down here, and then through a graphical representation, the concept of a keystone species by the interactions among these living systems within a given environment. Hopefully that makes some sense and you get a good sense of the concept of a keystone species as a result. All right, so what I want you to be able to do is predict the effects of a change in matter and energy available on a community. So in this case, I'm going to look at two different paramecium species and what happens when they both grow alone and when they grow together. And I want you to be able to predict, what do you think is going on within the community when both of them are present. So over on the lower left, we see P. aurelia, or Paramecium aurelia, when it's grown alone, and then we see the Paramecium caudatum when it's grown alone. And then when I grow both species together, what we see is the P. caudatum, or the Paramecium caudatum population, is really, really low. So what do you think the community interaction is going on between these two species? They're both paramecium species. What is a possible explanation as to why, when they grow together, we see so few Paramecium caudatum? Well, it turns out that when you grow them together, the P. caudatum is outcompeted for resources. And so this is showing competition as an example. So if your mind went to like, oh, the P. caudatum, they're being fed upon, but you could have gone a lot of different ways. But what we'd see is that if the P. caudatum was the food supply for the P. aurelia, we would see that once the Paramecium caudatum population went down, we would expect the P. aurelia population to go down. But the fact that one is able to survive really, really well when they're both present, and one is only able to thrive when the other is not present, suggests that these two are competing for resources and just one is better. This is going to give us the concept of competitive exclusion. You can't really have two organisms fill the same niche, and when we try to grow them together, the P. aurelia is just much better at competing for these resources than the P. caudatum in this given environment. And so as a result, from that competition, really only one of the two species thrives in this given environment. So again, hopefully we're able to predict what that relationship was based off that given data. I think a different way I could have shown you this is I could have shown you the two populations on their own and say, predict what happens when you grow them together. And maybe that would have been a fair way to predict the effects of changes on matter and energy. And maybe you wouldn't have been able to predict which one would compete, but if I told you that both of these organisms fill a similar niche, hopefully you would be able to predict that one of them would have thrived and the other would not have, because there's only going to be so many resources available and one species would be better able to fill that niche than the other. And that's really the take home that you should get, that matter and energy are going to have a finite availability in a given community, and when certain organisms come in, they're going to either be an advantage or disadvantage in a given community, and as a result, you're going to see populations respond appropriately. This is also a reason why when we talk about invasive species, oftentimes invasive species cause disruptions to communities, because an invasive species may be able to outcompete a native species and therefore is going to shift the distribution of those species present in a given environment. All right, I hope that was helpful, and I'll talk to everybody soon.